So in the first problem, we're looking at how much ethanol, or the most common biofuel, right, we can create from some sort of a biomass that we have, right? Something which has reasonably high sugar content. So here for this particular problem, we are told that for production of ethanol, we are dealing with a feedstock which is relatively high in sugar content, and this is first converted to sugar, which is glucose right here. Okay, and the sugar, which is glucose, is then fermented into ethanol, which is this part, right? This is ethanol, C2H5OH, through this reaction. Now, what we are told is we are told to consider 100 kilograms of sugar beetroots. This is our feedstock, okay? And its sugar content is 20% of the total mass. So 20% of the total mass of sugar beetroots is sugar or glucose, right? And the question is how much ethanol can you produce from 100 kilograms of sugar beetroots? Okay, so what we're looking for is something very simple. We have a certain feedstock, 20% of which is sugar. And the idea is we want to see how much ethanol we can produce from this 100 kilograms of feedstock. So it just requires us to go step by step, first from feedstock to sugar, and then from sugar to ethanol. Okay, and it has to follow the chemical reaction that we are providing. Now, to solve this problem, it's essentially looking at different masses for different chemicals involved here, right? So, or different uh, compounds involved here. So, uh, the atomic masses will be provided to you. So, we'll give you the atomic mass for carbon as 1 gram per mole or 1 kilogram per kilomole. Okay. For oxygen, either oxygen atom or oxygen molecule. For oxygen molecule, it is 32 kilogram per kilomole. And then for hydrogen, again, hydrogen atom will be 1 kilogram per mole, or hydrogen molecule H2 will be 2 kilogram per kilomole. Okay, so this information will be given. Okay, you don't have to remember this. So what we know from here is that for 1 mole of uh, glucose, we are able to produce 2 moles of ethanol, right? Now the question is how much is the mass of 1 mole of glucose, right? And once we know that, then we can calculate everything from it. So when we look at the molar mass for glucose, looking at the above formula, we can very easily calculate it. The formula for glucose is C6H12O6, which means it should have 6 carbon atoms. Sorry, the mass for carbon atom is 12 kilogram per kilomole, right? So 6 times 12 plus the mass for 12 hydrogen atoms or 6 hydrogen molecules. So 6 times 2 plus the mass for 3 oxygen molecule, right? Or 6 oxygen atoms. So this is an oxygen molecule, okay? So it has 2 oxygen atoms already. So 3 times 32. So when you do the math, the mass comes out to be 180 kilogram per kilomole. Okay, so this is for glucose. 1 kilomole of glucose weighs 180 kilogram. Same way we can do it for ethanol. So ethanol is C2H5OH, or you can write it as C2H6O, right? There is total of 6 hydrogen atoms. OH, this is also an additional hydrogen atom. So molar mass is going to be 2 times molar mass of carbon atom, which is 12, right? Plus 3 times the molar mass of hydrogen molecule, which is 2, plus the mass of oxygen atom, which is 32 by 2, right? So when you sum this up, comes out to be 46 kilogram per kilomole. Now, what we know from this chemical reaction is C6H12O6. 1 mole of glucose will give us 2 moles of ethanol, shown by this part here, C2H5OH, plus 2 moles of CO2. Now, we don't really care about CO2. What we care is 1 mole or 1 kilomole of ethanol of glucose is giving us 2 moles or 2 kilomoles of ethanol, right? Which means that if we have 180 kilograms of glucose, it's going to produce 2 times the molar mass of ethanol, or 2 times 46 kilograms of ethanol. Okay, this is the basic equation that we are looking for. So, which means that if you have 1 kilogram of glucose, it's going to produce 46 into 2 by 180, which is about 0.511 kilogram of ethanol. So this is the main equation. This is the main problem that we are solving, right? Once you know how much 1 kilogram of glucose will produce, how much ethanol 1 kilogram of glucose will produce, the second part is very simple. You're dealing with a feedstock, which is 100 kilogram in mass, and 20% of this feedstock is sugar content. So 20% of this is glucose, right? Which means that we are dealing with 20 kilograms of glucose. Okay, so 1 kilogram of glucose corresponds to 0.511. 20 kilograms of glucose will correspond to 20 times 0.511, which is about 10.2 kilogram of ethanol. Or if you want to, and well, okay, 10.2 kilogram of ethanol, which is the end of the problem, which is exactly what we are asking. But just to look at it in terms of how much it would be in terms of the liters, we're talking about 12.9 liters of ethanol. Now, you do not have to convert the kilogram into liters. I'm just giving that as an additional information, but this is where the problem ends, right? So you formed 1 kilogram of glucose will always give you 0.511 kilogram of ethanol, okay? And it does not really matter what is your source of glucose, right? The source of glucose can be sugar cane, sugar beet, or any other source. Uh, the 1 kilogram of glucose will always give you 0.51 kilogram of ethanol. Now, where your feedstock matters is how much is the content of glucose within that feedstock. For this particular feedstock, sugar beetroots, the content was 20%, right? 20% of the total mass, which means that 100 kilograms of sugar beetroots will give us about 10.2 kilograms of ethanol. But let's say you have another feedstock which has a higher sugar content, maybe 30% sugar content, right? 30% of the total mass is sugar. Then it'll basically give you a much higher content of ethanol as well, starting from the same mass of the feedstock. So this is why we always say that if you want to pick up a feedstock, you always have to make sure that it has high sugar content, because high sugar content simply means that for the same mass of the feedstock, you are able to produce more ethanol. Okay, so this is basically the end of problem one, and this is how we solved it in the class as well. And this is just the type solution for what we just discussed. Now let's move on to the next problem. Okay. Now in this problem, what we are provided is we're dealing with an ethanol engine. It's a very specific problem, right? It may or may not present what will happen in reality. So here we are looking at a very simple 1.6 liter gasoline engine, internal combustion engine, and it's producing a maximum power of 100 kilowatt when fuel is burned stoichiometrically with air. Okay, so when fuel is burned stoichiometrically with air, so we are talking about sort of complete combustion. And to keep things simple, we are just talking about complete combustion with the exact amount of air that is needed for combustion. Okay. Uh, and what we are told is the thermal efficiency is given. We said thermal efficiency is 38%. Okay. Now, what we wanted was we want to estimate the maximum power from this engine if we use ethanol as a fuel instead of the gasoline. All right. And we are told that ethanol also burns or undergoes stoichiometric combustion and has the same thermal efficiency. Okay, so that's the constraint that we are putting. Once we calculate the power that you can get from the engine if you burn ethanol instead of gasoline, once we do that, we also have to determine what is the rate of consumption of gasoline and ethanol for producing this maximum power. Okay, to make it simple, the stoichiometric air fuel ratio for gasoline is given, and we are assuming combustion efficiency to be 100%. All right, so this is the problem that we're looking at. Now, a formula that we very frequently use, and this, by the way, is something that you do not have to remember. It's something that's that'll be given to you is that when you're looking at any engine, right, the power produced from that engine is directly proportional to the heating value of the fuel that you're having, okay? And it's inversely proportional to the air fuel ratio, right? So this is something that we're given, and this applies as long as you're looking at something with a fixed volume. So same engine volume for the for engines of the exact same volume, you can very easily calculate the effect of changing the fuel on the power produced by looking at this particular formula. Okay, and if it's proportional, right, it basically means that you can convert this proportionality into equality by taking a ratio. So the power output from engine 1 divided by engine 2 for the same volume is equal to LHV1 by AFR1 for different fuels, basically, divided by LHV2 by AFR2. Okay. So it's as simple as that. And that's essentially what we will be doing here. Okay. Now we have the power output given for gasoline. We want to find out the power output for the engine where when we burn ethanol. So let's say we want to find W.2. And the heating value, of course, should be given to you and will be provided to you. The air fuel ratio for gasoline is already given. We need to find the air fuel ratio for ethanol. So essentially, we want to find W.2, but for finding that, we need to find first the air fuel ratio. Okay, and for the air fuel ratio, we simply need to write down the chemical reaction equation. All right. Now, when we are looking at it, basically, uh, here we're looking for ethanol, right? But let me explain it to you for any, for any fuel. So for any fuel, when we say stoichiometric combustion and stoichiometric and complete combustion, which is the only case of combustion we are considering, by the way, in this course, just for simplicity, right? In reality, we don't have stoichiometric combustion, but for simplicity, we are considering this very simple case of combustion. So for any fuel that's undergoing stoichiometric combustion with theoretical air, which is the only case we consider, any fuel that you take plus air plus some amount of air, A times air is always O2 plus 3.76 N2, will give you some amount of CO2 plus some amount of water vapor plus the exact same amount of nitrogen that you had on the reactant. So it is 3.76 A times N2. So this is a very general formula that you apply for any fuel. Okay. So once you have the fuel, then you will be able to find out B, D, and A. And once you have the value of A, then you can simply go ahead and calculate the air fuel ratio. And the air fuel ratio basically is the ratio of air to ratio of fuel in terms of the mass, right? Not in terms of the moles. So first we need the chemical reaction equation to find the value of A, and then we can we can use the molar masses. Now, another very key important point about complete combustion is that all the carbon in the fuel gets converted to CO2. All the hydrogen in the fuel gets converted to H2O. Okay, so based on the fuel that you're provided, you can very easily calculate the values of B and D. It's a very straightforward thing. So now let's apply this for the fuel that we are looking. The fuel that we have here is ethanol, right? So this is the fuel we are looking for, C2H6O or C2H5OH. Okay, so let's write C2H6O plus some amount of air should give us some amount of CO2 plus some amount of H2O plus 3.76 A times N2. Now we don't really care about nitrogen for now because our main target is to get the value of A. Now, when we look at it, we have two carbon atoms on the reactant side, okay, in the fuel essentially. Two carbon atoms are available here, which means that we should have two carbon atoms on the product side. The only place where we have carbon is CO2, as just mentioned here, right? So it should just be 2 times CO2, two carbons, and that's it. Okay, we'll fix oxygen a bit later once we have taken care of hydrogen and carbon. We have 6 hydrogen atoms on the in the fuel, right? Which means that we should have 6 hydrogen atoms on the product side as well. All the hydrogen, as we said, shows up only in H2O. So we have 2, so 3 times 2 is 6. So now we have ensured that we have 6 hydrogen atoms, all of them located in the water vapor, and we have two carbon atoms, all of them located in CO2. Now let's try to balance the number of oxygen atoms. Okay, so if you apply atom balance for oxygen, then what we have on the reactant side is basically oxygen in the air, so 2A, plus also the oxygen in the fuel, okay, plus 1. So 2A plus 1 is equal to, we have oxygen in carbon dioxide, so 2 times 2 is 4, right? 4 oxygen atoms, and we have oxygen in the water molecule as well, so which is 3. So basically from here, what we can very easily see is that 2A comes out to be equal to 6, or A is 3. Okay. And this is essentially how we balance the chemical reaction equation. So once you have the value of A, then the air fuel ratio is what we were after. Air fuel ratio is the mass of air by mass of fuel, right? So number of moles of air are basically this value A, which is 3, times 4.76. 1 mole of oxygen, 3.76 of nitrogen. 3.76 plus 1 is 4.76. Okay. This is the number of moles for air divided by the number of moles of fuel. We just have 1 mole of fuel, right? It was just 1 here. So this is the molar air fuel ratio. Now you need to multiply it with the molar masses for air and molar mass for the fuel. Okay. So let's go back here. We're looking for air fuel ratio, and we said it's mass of air by mass of fuel. And in terms of the molar, the number of moles of air, we got it from balancing the chemical equation, which was C2H6O plus 3 times O2 plus 3.76 N2 was giving us 2CO2 plus 3H2O plus 3.76 N2. Okay. Now the mass of air is number of moles of air, which is 3 into 4.76 by number of moles of fuels times the molar mass of air, how many kilograms you have in kilomole of air, divided by the molar mass for the fuel. Okay. Now again, the molar mass for the air will be provided, right? It's to be specific, it's 28.4, but you can also take it as 29, right? So 3 into 4.76 by multiplied by 29 molar mass for air divided by molar mass of fuel. Now, molar mass of fuel is something you can calculate based on the the masses for different atoms for carbon, hydrogen, and oxygen. We did it in the previous problem, so we'll just take 46 as it is. So this comes out to be 9. Okay, so now we have the air fuel ratio for this particular problem, and this is in terms of the mass. So air fuel ratio for ethanol simply tells you that for 1 kilogram of fuel, of ethanol fuel, we need 9 kilograms of air. Okay, for ensuring that the combustion is stoichiometric and complete. Now, that's one main problem done. This allows us to proceed to the next step, which is it allows us to basically go ahead and make use of this formula to calculate the power output for ethanol, right? We have the heating values. We had the AFR already given for gasoline, and now we calculated the AFR for ethanol, which is right here. Okay, so let's go ahead then. Right, so this is again what we just discussed. This is how you balance the chemical equation, and you have the air fuel ratio. Now, once you have the air fuel ratio, we wrote the formula before that W, the power output for gasoline by power output for ethanol, is going to be low heating value for gasoline by air fuel ratio for gasoline divided by low heating value for ethanol divided by air fuel ratio ethanol. Okay. Now we have the low heating value will be provided to you, so you don't have to remember it. It's 43,000 for gasoline, and the air fuel ratio was 14.6, already given in the question, right? divided by the low heating value for ethanol. Again, it will be provided to you. It's 26,950, about half of what it is for gasoline. And the air fuel ratio, we calculated it, right? It's 9. So when you do the math, this ratio comes out to be 0.984. So using this, we can simply say the work output for ethanol, for using the same engine with ethanol fuel, is the work output for gasoline divided by 0.984, or it comes out to be 101.7 kilowatt. Okay, so this is uh, taking care of the first part of the problem. Now, once you have the maximum power, we want to calculate what is the rate of consumption of gasoline and ethanol for this particular maximum operation. Now, when you look at the thermal efficiency, it's provided to us, and it is the net work output divided by heat input, right? For any engine. Now, work output is given to us for the same engine with different fuels. We need to calculate the heat input, right? And we know the thermal efficiency, and it is said that it's same for both. Now, what is the heat input? Well, the heat input comes from burning the fuel, right? So the heat input will be basically equal to simply the mass of the fuel, or the mass flow rate of the fuel at which you're consuming it, times the low heating value of the fuel, which gives us how much energy can be obtained by burning that fuel, by burning a kilogram of that fuel, right? So here, this 43,000 that I told you about is the heating value, and this is 43,000 kilojoule per kilogram. So it tells you that if you burn 1 kilogram of gasoline, you can get 43,000 kilojoules out of it. So this m dot fuel times low heating value gives you the heating value that's available from the fuel. But sometimes, depending on the combustion efficiency, not all of this is available to the engine. In this case, the combustion efficiency is 100%, which means that the product of mass flow rate of the fuel times heating value will give you Qn directly. Okay, so this is what we need to apply for both, right? So we are looking at the we're looking at this basic formula. We'll have to do it one by one. So first, let's do it for, let's write Qn as work output by thermal efficiency. Okay, you have different work output for uh, gasoline and different work output uh, for ethanol. So when you do it for when you write it down, the heat input for gasoline is mass flow rate of gasoline times low heating value for gasoline into the combustion efficiency. Combustion efficiency is the same for both. So this is 100 kilowatt or 100 kilojoule per second divided by 0.38, which is the thermal efficiency. Okay, this one is combustion efficiency. Combustion efficiency is 100%. So here I'm simply looking for mass flow rate of the gasoline. So mass flow rate of gasoline is 100 kilojoule per second divided by 0.38 times the heating value, 43,000. When you do the math, this comes out to be 0.00612 kilogram per second. Okay, so this is the amount of gasoline that you use. Now we can do a very similar calculation for ethanol as well, right? And what you will see is that for ethanol, let me do that here. Now for ethanol, it's essentially the same thing, right? The only difference is the power output is different. And of course, the heating value is different. Now for ethanol, uh, Qn, as we said, mass flow rate of ethanol, low heating value for ethanol times combustion efficiency. Combustion efficiency is same. The work output for ethanol is different, 101.7, but the thermal efficiency is same, right? 0.38. Now, if you want to find out the mass flow rate of ethanol, you simply have to divide this number, 101.7 by 0.38. You have to divide it by the low heating value for ethanol, which is pretty small, 26950, and combustion efficiency is 1. When you do the math, this comes out to be 0.0099 kilogram per second. Okay, so it's just as simple as that. Now, in this particular case, well, you can simply note that when we calculate the mass flow rate for the two fuels, the mass flow rate for ethanol is much higher than the one for gasoline. And the reason it's higher is because we have a very low heating value for gasoline, right? It doesn't produce much amount of heat when it's for the same weight of fuel. Okay, which is why we need more of the fuel just to produce a given amount of heat. So that's this is what we see in this particular problem, and this is basically the end of this problem.